So let's prepare the solution of nickel 2 sulfate. I've got a bottle of nickel 2 sulfate hexahydrate, and we're going to add some to a weighing boat on the electronic balance to prepare our standard solution of nickel sulfate. So I'll put the weighing boat on the balance. I'll zero the balance so it ignores the mass of the weighing boat. And now I'm going to add some of the solid nickel sulfate. When you're weighing things like this on a balance, it's good to hold the bottle right above the balance, right above the weighing boat, so that if you do spill something, it goes into the weighing boat and not onto the balance. So I'm going to keep adding here. I've got a certain mass in my mind that I want to use. Okay, I'm getting close. All right. A little bit more. There you go. All right. So there's the mass of nickel 2 sulfate hexahydrate. You can record that mass, and I'm going to use it to make 50 milliliters. I've got a 50.0 milliliter volumetric flask. I'm going to make a 50 milliliter solution with this. All right, to make the solution, we take the volumetric flask. Remember that a volumetric flask is different from a normal Erlenmeyer flask. It's much more accurate, and it's designed to measure only one volume precisely. They have this characteristic shape of a rounded bottom and a long, narrow neck. On the neck of the flask, there's one line. That line, if you filled it up so the meniscus is on that line, would represent 50.00 milliliters of a solution at 20 degrees Celsius. So I'm going to take my nickel sulfate, I'm going to carefully transfer it to the flask, and you don't want to spill any, otherwise the care with which you just massed everything would be messed up. Now I've transferred almost all of it, but you can see there's still some nickel sulfate in the weighing boat. So I'm going to add some distilled water to the weighing boat, and I'm going to include that into my flask. Okay, I want to get all of that nickel sulfate into the flask without spilling any. There's a little bit more, one drop, or so let's do one more time with a bit of distilled water and add that to the flask also. All right. There's a tiny little bit left on the edge of the weighing boat, but I'm going to let that go as a small source of error. So I've got the mass of nickel sulfate in the flask with a little bit of distilled water. I'm going to add some more distilled water until the flask is approximately 1/3 to 1/2 full. Okay, at this point, you don't want to fill the flask because we're going to want to shake it up to dissolve it. So it's about 1/3 full. I put the stopper back on the flask, and then I'm going to shake it very vigorously. If you had filled it all the way to the line at this point, you wouldn't be able to shake it very well and dissolve the salt. So you're going to keep shaking it in a circular motion. Try not to get any of the solution up the neck of the flask at this point. So you're just trying to dissolve it. You're going to keep doing this until the salt is fully dissolved. All right, after shaking for about 3 or 4 minutes, every crystal of the salt is now dissolved. Looking from below, there's no evidence of any solid left, and there's no solid around the edges of the flask. So now I'm going to remove the stopper. I'm going to wash down the neck of the flask just in case any nickel sulfate solution got up there. And then I'm going to add water, distilled water, until I am very close to that line on the neck of the flask. Okay, so keep adding distilled water until you are just about at the neck at that line. So I'm about 1 centimeter or 1/2 centimeter below the line on the neck of the flask. I want to get the meniscus perfectly touching that line, the bottom of the meniscus. So I'm going to put some distilled water in a beaker at this point. I'm going to use a plastic disposable pipette. Looking at eye level, I'm going to keep adding the distilled water until the meniscus is just touching the line on the flask. All right, so the bottom of the meniscus is now perfectly touching the line, and I'm almost done making my solution. But right now there's lots of distilled water at the top and solutions down here at the bottom more concentrated. So I'm going to turn it upside down with my thumb on the stopper. I'm going to shake it, turn it back like this, take the stopper out for a moment to let it breathe, put it back in, and I'll repeat that mixing about 3 times. So there's 2, let it breathe, and 1 more time and we'll be done. So now my solution is perfectly mixed, and I've got 50.0 milliliters of solution in this volumetric flask. While we're looking at the solution in the flask, we can see some evidence of one aspect of the Beer-Lambert Law, Beer's Law. Beer's Law tells us that 2 variables affect the absorbance of a solution. The absorbance refers to the amount of light absorbed by the solution. When you have a flask like this, which is wide at the bottom and narrow at the top, you see evidence of one of the 2 variables that affects the absorbance. Down here at the bottom, I'm not sure if you can see that clearly in the video, but the solution is darker green. The nickel sulfate gives it a green color, but it looks darker down here than it does in the narrow neck of the flask. The reason for that is that the distance that light passes through the solution is one variable that determines how much light is absorbed by the solution. Down here it's wider, so light travels for a longer distance through that part of the flask, through the solution, so more light is being absorbed and it looks darker. Up here it's narrower, so the path length, the distance the light travels through there, is less, shorter distance, so therefore the amount of light absorbed is less, the absorbance is lower, and it looks lighter. So it looks darker, it looks lighter, more light is absorbed here, less light is absorbed here. It's the same solution everywhere, the only difference is the path length, the distance the light is traveling through the solution. The other variable in Beer's Law, the Beer-Lambert Law, that talks about absorbance of solutions is concentration. I've got a second solution here of nickel sulfate. Here's the one we just prepared on your left, and here's the one that I've got here on the right. It's different. Can you tell just by looking at them that they have different concentrations? The flasks are very similar in shape, so we could ignore the distance variable that affects absorbance. But is it obvious to you that this flask here on your left is more concentrated solution than the one on the right? I hope it is, because most of us intuitively know that when you're making a colored drink at home, the darker the color, the more concentrated it is. So when a solution is more concentrated, it looks darker, and that's because more and more light is absorbed. So the second variable that affects the absorbance of a solution is the concentration. Higher concentrations have greater absorbance of light, and they look darker. Lower concentrations absorb less light, and so more light is transmitted through the solution, and therefore they look lighter. So you can rank solutions' concentrations by just looking at their colors like this, as long as the path length, the distance the light's traveling through the solutions, are similar. All right, in this next part of the experiment, we're going to calibrate a SpectroVis spectrophotometer. The spectrophotometer is here. It's made by Vernier. SpectroVis is a spectrophotometer, which is a device which shines light of any wavelength you'd like, or in what we're about to do, it'll shine light through an entire region of wavelength. So we're going to use visible light from 400 to about 750 nanometers. We're going to shine that light through a solution, and it'll measure how much light is absorbed by the solution and display it on the computer screen there. I'm using a cuvette, which is like a little plastic test tube. These cuvettes are square, and they've got ridges on 2 sides which you can handle, and they have 2 sides which are clear, colorless, through which the light will pass, so it's not a good idea to touch there. It always has a little cap on them. So I've got one of these already filled with some distilled water. Remember that we made our nickel sulfate solution by dissolving it in distilled water. And distilled water, even though it looks colorless, it does absorb some light. If you've ever seen somebody travel deeper and deeper in the ocean as they go diving, you know that it gets darker and darker the deeper they go. It gets darker because the water is absorbing some light, even though the water might look colorless if you scooped some up in your hand. So we're going to get the computer to ignore the absorbance of the water, which is in our solution, and measure only the absorbance of the nickel sulfate, or more specifically the nickel 2+ cations. So I filled the cuvette with distilled water about 3/4 to 80% full. I'm wiping it off with a special tissue called a Kim wipe, which will not scratch the plastic. And then I've got the cuvette with distilled water. I'm putting it into the SpectroViz spectrophotometer. I've put it in a way that the clear sides are lined up with the path length of the light. So there's little symbols here that tell me the light is traveling this way, so the light will go through the clear sides of the cuvette. And now on my computer interface, I'm going to tap and I'm going to select the calibrate option. We would like to have it ignore the absorbance of the distilled water that's in our solution. So we're going to let it warm up for a few seconds, and then we'll finish the calibration. All right, so now that we've finished the warm-up period, we can finish the calibration on the computer. Press Finish Calibration. And when it's done, it'll just take a moment. We press OK to go back to the main screen. And at this point, the SpectroViz will be ignoring the absorbance of distilled water that's in our solution. So I'll take that cuvette out. I'm going to discard the distilled water. I've got a waste beaker here. I've taken the solution of nickel sulfate that we prepared earlier, and I've poured it into a small beaker. So I'm going to just pour a little bit of that into the cuvette that had distilled water in it. And I'm going to shake it up, and I'm going to discard that because it had some distilled water in it. And I'm going to now, normally I would do that 3 times, but because of what we're going to do next, the exact concentration is not critical. I'm going to wipe off the cuvette, get rid of any liquid that might be on the outside. I don't want to damage the SpectroViz. Also inspect the cuvette for any bubbles. You don't want any air bubbles in your cuvette. If you see them, you just flick it to get rid of air bubbles, and make sure there's no fingerprints and things like that on the clear sides. Anything that would obstruct light will affect the absorbance value. So I put that into the SpectroViz in the same way that the light passes through the clear sides. And on the computer interface, you may be able to see that the option for full spectrum has been selected. That means we're going to be able to see the absorbance of the solution through the entire spectrum. So I press collect. I'll discard some old data. It takes just a moment. This particular experiment used to take about an hour to do with an older device. So I'll press stop. And now on the computer screen, I hope you can see the graph that's been produced. I'm going to remove. So I've adjusted the scale on the x-axis of this graph. So now it's going from 400 nanometers, which is usually thought of as the beginning of the visible spectrum, up to about 750 nanometers, which is the end of the visible spectrum. And you can see laying over top are the colors of the rainbow, which represent the different wavelengths. Now, if you look carefully, we're looking for the wavelength of maximum absorbance. We'll call that lambda max. The Greek letter lambda is used to represent wavelength, and lambda max means the wavelength of maximum absorbance. So looking on this graph, there's a point right about here, at about 722 nanometers, which looks like it has the highest absorbance value. Its absorbance is about 0.95. So that's the wavelength that I'm going to use. If you were using a colorimeter instead of a SpectroViz, the colorimeter would have only 4 options for wavelengths for you to choose from. And you would choose the wavelength on the colorimeter that was closest to lambda max. Now, just a quick note about the shape of the graph. Remember that our solution is green colored. That means as all the different wavelengths of light enter the solution, the green colors, the green region of the visible spectrum, is being transmitted. The green colors are coming through to our eyes, and that's what we see. So if green colors are coming through, they're not being absorbed, then when we look at this graph in the greenish region of the spectrum, notice the absorbance values there are the lowest on the graph. So the absorbances are lowest in the region of the spectrum that represents the color that we see. So on a color wheel in an art class, if you're an art student, you may have seen a color wheel before. Opposite the green region of the color wheel, there should be a reddish-orange region, and that's the region that would have the highest absorbance values for this nickel solution, this green-colored nickel solution. So we're going to use a wavelength. I'm not sure if this contradicts what I said earlier, but I'm going to use about 727, 730 nanometers is what I'll use as my lambda max. So what I'm going to do next is I'm going to take the original nickel sulfate solution that we prepared, the dark green solution. I've got it in a beaker. I'm going to take that and pipette it into 5 different test tubes. I'm going to dilute the solution to create 5 different concentrations. Now you saw earlier the mass of nickel sulfate that I used, and you saw the volume of the flask that we used. So you're able to calculate the concentration of this starting stock solution of nickel sulfate. What I'm going to do now is dilute it by putting 2 milliliters, 4, 6, 8, and 10. So one more time, 2 milliliters, 4, 6, 8, and 10 milliliters of nickel sulfate into the 5 test tubes. And then I'm going to add distilled water to get 10 milliliters total in each one. So I'm using a pipette. This is a Mohr pipette. It's called a Mohr pipette, M-O-H-R. It's got calibrations from 0 milliliters down to 10 milliliters. So it can deliver anything from 0 to 10 milliliters. So I'm going to put it in my beaker till it's near the bottom. I've got a pipette bulb. I squeeze the air out and I press down on top of the pipette. I lift it slightly off the bottom, and then while still pressing on the pipette bulb, I slowly release my grip, and the liquid in the pipette should be rising up. There it goes. Now it didn't rise all the way, so I'll put it back on the bottom, squeeze the air out, and I'll repeat that. I want to get the liquid level up above the 0 line. There it goes above 0. I'll take the bulb off, and you saw me put my finger on. Now I'm going to take the beaker, I'll lift the pipette out of the beaker, and I'm going to look at eye level and adjust the meniscus by releasing the pressure on my finger at the top. I'm going to release the meniscus, release by pressure rather, to get the meniscus to drop, and it's below 0. So I'm going to let it drop till it reaches the 1. So it's going to drop, 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 and now it has just perfectly reached the 1. So I'm going to touch any drop that's on the end of the pipette to the side of the beaker. I'll grab my first test tube. I'm going to put 2 milliliters in here. So the meniscus right now is at 1 milliliter on my pipette. So to get 2 milliliters, I'm going to let it drop from 1 to 3. So now it's dropping from 1 to 2 to 3. And when it reaches 3, I'm going to stop perfectly, touch the edge of the pipette to the glass to get rid of any drop, and I've just put 2 milliliters of solution in here. So I'm going to repeat that process and put 4 milliliters in here, 6, 8, and 10 milliliters in this last test tube of the nickel sulfate solution. All right, so I've just finished pipetting the nickel solutions into the 5 test tubes. Now I've got another beaker here with distilled water in it. So I'm going to now pipette distilled water into each test tube to make the total volume 10 milliliters. So if there's 2 milliliters of nickel sulfate already in the first test tube, I'm going to add with another pipette, a clean pipette, 8 milliliters of the distilled water to get a total volume of 10. The second test tube has 4 milliliters of the nickel sulfate solution, so I'll add 6 milliliters of distilled water to that test tube. So in the end, I'll be putting 8, 6, 4, 2, and the last test tube already has 10 milliliters of nickel sulfate, so I won't be adding any distilled water to that one. Just let me show you one more time what I'm doing. The pipette goes in the bottom of the beaker of water, so it's near the bottom. I put the pipette bulb, squeeze the air out, push firmly on the top. I have to press firmly to make a tight seal. I hold the pipette near the bottom like this, and then I slowly release the grip on the pipette bulb. I've lifted it off the bottom of the beaker. Now I'll put the 2 milliliters in the 4th test tube here. So I'm going to lift the pipette out of the distilled water. I'm holding it vertical, and I'm going to let the meniscus fall until, in this case, it's going to reach 6 milliliters. So there it is. It's at 6 milliliters exactly. I touch the side of the beaker. I'll grab the 4th test tube, which has 8 milliliters of nickel sulfate, and I'm going to put 2 milliliters of distilled water. So if the meniscus in my pipette is at 6, I'm going to let it drop until it reaches 8. From 6 to 8 means 2 milliliters will have been added. Now be sure you're looking at eye level when you do this, and you want the meniscus in the pipette to be touching the 8 perfectly. Touch the pipette again to the side of the test tube to get rid of any outside water, and now I've just put 2 milliliters of water in here. So I'm going to repeat that, and I'll put 4 milliliters, 6 milliliters, and 8 milliliters of distilled water to create 5 different dilutions of my nickel sulfate solution. So I finished pipetting my solutions, and I've now got 5 dilutions in these test tubes. I've got 2 milliliters of nickel and 8 milliliters of water here. I've got 10 milliliters of the nickel solution here with no water. And you can tell, I think, I'm not sure if you can easily see this in the video, but the levels of the test tubes are all roughly equal, which means they all have about 10 milliliters in them, which they should. And the colors, this first one looks much lighter than this last one does. So the colors go from light to dark, which means the concentrations are going from lowest to highest in those 5 test tubes. So what we're going to do next is fill 5 cuvettes. Ideally, I'd be using the same cuvette for each one, but for simplicity in this video, I'm going to use 5 different cuvettes, which will be a small source of error. I'm going to take 5 cuvettes and I'll fill each one with a solution, and then we're going to measure their absorbance values at lambda max. Then we're going to take an unknown solution of nickel sulfate, a solution whose concentration your job is to figure out, and we'll measure its absorbance value also. All right, so as I said earlier, ideally you would use the same cuvette that you had used to calibrate your SpectroViz when you're measuring the absorbance values of the solutions, because the cuvettes can have small imperfections that make them different from each other. So something that gives an absorbance value in one cuvette may have a slightly different reading in a different cuvette. For simplicity's sake, I've used 5 different cuvettes for the 5 solutions, and I've got a 6th cuvette for our unknown solution as well. Now I've already checked the cuvettes to make sure there's no air bubbles in them, and I've dried them all as well. So at this point, I'm going to simply put each cuvette in the SpectroViz. It has already been set to measure the absorbance values, which you'll see on the iPad interface, and it's measuring the absorbance values at the lambda max value that we saw earlier. So as I put each one in, you're going to want to look at the computer interface and record the value that you see. So let me just go back to the main screen here. All right, so putting the first one in, this is the least concentrated nickel sulfate solution. You can see on the computer interface the absorbance value at 727 nanometers. So record that first reading. Now we'll take the second dilution and we'll measure its absorbance value. Again, be sure you're putting it in so the clear sides of the cuvette are lined up with the path of the light. Record that absorbance value. The third test tube's absorbance value. And the fourth test tube's absorbance value. You can see the absorbances are increasing, which makes sense because the solutions are getting darker and more concentrated. And then the last test tube's absorbance value. So these are the absorbances of the 5 solutions whose concentrations you should know. You should be able to calculate them. And now we're going to measure the absorbance value of the unknown solution, and you'll have to figure out this concentration yourself. So this 6th absorbance value is the unknown's absorbance value. There you go. Now one thing I didn't mention earlier that's important for Beer's law is that the width of these test tubes, the diameter of the test tube, is exactly 1 centimeter. So in the Beer's Law equation, the value for B, the path length, would be 1 centimeter in all of these cases. So there you have it, 5 solutions of nickel sulfate and their absorbance values, and an unknown nickel sulfate solution and its absorbance value. You should be able to take this information and create your Beer's Law graph. From that graph, you'll do linear regression to get the equation of the line of best fit, and then you'll use that equation to figure out the concentration of this 6th solution, this unknown solution. So good luck, Beer's Law.